Yeah, so the feedback summary for what are the gaps, for what the key questions, it was about consistency and model standardization, and how broadly they're deployable. How can we clearly communicate model limitations? For model comparisons, how should we be choosing inputs for these models? And further documentation would be great. Open science, so how can we leverage what other fields are doing to make sure that we are building codes that we can all use and build up of. For future features, making sure we can do things like vapor bubbles and integrating with other data sets, including disequilibrium processes and kinetics. How can we encourage collaboration among larger groups? The lack of experimental data for intermediate compositions and halogens. For challenges and potential solutions, for volcano monitoring, modeling isn't straightforward because many of the parameters are poorly known. A funding issue, so getting funding for experiments can be challenging. And can we use something like bigger, broader community efforts to try and do this? How do we make sure that we kind of highlight that intermediate compositions have this direct link to hazardous arc volcanoes and economic geology? The publication rate can be slower as experiments take a long time and don't always work. Disequilibrium experiments are complicated and it's hard to get the gas composition. Controlling FO2 is difficult. Different lab setups mean we get different results. How to measure the exol phase. Oh, and amphibole adds complications. Yeah, we haven't really discussed solid phases really at all today. So maybe that's something to bring up. And then a target area to tackle these questions. So disequilibrium, more experiments, having a wider composition, focusing on intermediate compositions, and an effort to maybe reanalyze existing run products so we can kind of extract more information from experiments that have already been done. So is there anything either online or in the room that anyone wants to kind of comment on? Maybe something that hasn't been brought up before that you've now thought of? So if in the room, you just put your hand up, and online, also you can raise a virtual hand. Anything people want to highlight?
Today we've talked about some really wonderful benchmarking work that's been done in the water and CO2 realm, and doing further benchmarking within sulfur would be a good area of development.
Yeah, great comment there.
It's a great point we discussed on, oh, sorry, you go.
No, go for it, Penny.
I was gonna say, it's a great point we discussed on WhatsApp during the lunch.
Yeah, a lot of these sulfur models are pretty recent. I think a lot of people during lockdowns when they couldn't get into the lab were like, we'll tackle the sulfur problem. So there's been a real explosion recently for that. Any other comments, either online or in the room? One for me would be the solid phases we haven't really touched on much. So obviously there's the melt gas equilibrium, but then we've had a little bit about like sulfide melts and maybe anhydrite or graphite. But then if you add something like amphibole to the mix or apatite, we really struggle to have models that incorporate all of those phases for sure. So, but I know there's a lot of experimental work going on for those solid phases, but yeah, I just kind of ignore crystals in what I kind of do.
And just to like add to that, this is a problem we found with VTCal too, is the temperature sensitivity of these like solubility relationships aren't very well known. And that's because almost all of the experiments are done above the solidus, because you don't want crystals involved in your volatile solubility experiments. But then you're obviously modeling in a melt inclusion, which is by definition below the solidus. So you're modeling at a temperature which is outside the range the model was calibrated at, almost by definition of how we're doing the experiments.
Yeah, that's a really great point. Got a comment in the room?
I'm just doing a PhD, so not an expert. But I guess we've talked a lot about like that gap in intermediate compositions, but my work looks at methylene normative systems, and I can't really access any kind of modeling in a lot of my work because none of it's calibrated that far under saturated direction either. So I guess from my perspective, talked a bit to other people working in Edinburgh, it's a key thing that I'd be keen to explore.
Yeah, great point there. Any further? One comment was about kind of the lab side of, well, kind of getting funding for these kind of experiments. Is that, I mean, one problem is getting funding to build labs. So for instance, here in Aotearoa, we don't have any high pressure, high temperature labs. We have a high pressure, high temperature fluid lab up in Wairaki, but that's, you know, bars and maybe 300 degrees C. But for the kind of stuff I want to do, we don't have the facilities here. So I imagine that's also a problem for a lot of people, is accessing the facilities to be able to do these kind of experiments. We're lobbying GNS, me and Jeff. We'd love some little cold seals to start with.
Can I make a comment, Ari, just back to the issue of temperature dependence?
Yep.
First of all, it's very small, and so it's hard to measure without a big temperature range available to you, and you'd have to go up over a range of several hundred degrees probably to be able to do it well. There are ways of inhibiting nucleation of crystals at lower temperatures, and that might help. There is one very interesting aspect of this, and at least for water, you know, most things have a negative temperature dependence of solubility, which basically means that if you heat something up, it'll boil. However, at elevated pressure for water, it reverses direction. And this has not been all that well studied, but would be very interesting, because it means that there's a depth limit to being able to generate the bubbling by intrusion of hot magma below. This was something Steve Sparks pointed out a long time ago. So, but it's just a hard measurement to make. That's all I would say, unless you can get to very high temperatures because it's such a small effect.
I think that's a great point. What we found with the models is, even though it should be small, some of them have been like empirically calibrated the temperature effect. And if you even slightly extrapolate it, you actually end up with a really strong effect, even though we think experimentally it's not that strong, which is also a concern.
It's probably because it's probably tied up with the uncertainties in the measurements, and then you extrapolate something with a lot of error.
Yeah, for sure. They're modeling temperature within a 50 Celsius range above the liquidus, and then when you extrapolate down to natural systems, you end up in trouble.
Yeah, great points there. Any other comments to bring up? Okay, in that case, I think I'll hand over to Echo. Did you have anything to share, or just some comments?
Yeah, do you want me to read out the whole summary here, or
Yeah, go for that.
Yeah, it's on the same document, just scrolling down. Well, wait, who's sharing the screen? I can share. Actually, I can share.
Ethics. I'm still trying to write the.
Okay, yeah, sure. Okay, let me get screen back. All right, share. So, okay, here we go. Can everyone see my screen here?
Yeah, we can see it here.
Is it big enough, or it's too small?
That's all right.
Okay, cool. I guess so. So this is the summary for what do observational researchers need these codes to be able to do. I kind of grouped them. What are the key open questions or needs related? So the first is how to link the geochemical modeling to the gas observation and geophysical observations. And then in terms of model usage, there are a few questions, I guess. So first of all is how to deal with the discrepancies between models and which model to use. What are the errors and uncertainties? And maybe there's a need for a working, there's some problems working across the platforms that need a universal language here. And more community supports like forums, YouTube videos, tutorials, regular workshops, hands-on demos in conferences to help people use the models. And then better documentations in the code, comments on the code, and common input and output files that can be compared. And also many models try to move towards integrating into one system like VESICAL, and comparisons among models are needed. And also questions about how to maintain the code and the legacy accesses. There are also requirements for more clarity on all major elements range for calibration data and the issues with the calibration data and the usage applied data. And then a graphical user interface would be more user-friendly. And then questions related to expansion of the existing models include sulfur, halogens, other trace gases that can be actually measured in fluxes and also brine phase, including sulfur and carbon isotope fractionation during degassing, including intermediate alkaline lignite compositions, including apatite, used as a tool to back out volatile behavior with well-calibrated models, including function to account for magma recharge on volatiles, how that impact volatiles, how to treat the supercritical fluids and gases, dealing with the disequilibrium behavior, and more experiments are needed on this regard. Calculate the gas, including calculate the gas speciation and calculate the FO2 along degassing. And speciations like carbon in very reduced magmas, and models that being able to batch process the multi-inclusion data and integrating the vapor bubble correction and the post-entrapment modification correction. And on the experimental fronts, maybe more multivalent, multi-component system involving chlorine and fluorine are needed for experiments. To predict the volcanic gas composition needs experiments between 1 atmosphere and a few hundred bars. Revisiting old experimental data and run products, reanalyze them. And there are also analytical challenges between labs. So what is the, regarding this topic, what is the potential target area where a multidisciplinary study could take place? So first of all, somewhere there is a lot of historical constraint data, philosophically close to vulnerable communities, intermediate composition, potentially for combination of experimental monitoring studies, maybe multidisciplinary works, including all 4 types of studies should be more of a focus. So basically combining experiments, monitor, and the sulfur and halogen bearing phases, like apatite, as mentioned before, and looking at some disequilibrium processes, and check a few otherwise very well constrained volcanoes, and designated developer team with stable funding, and develop a best practices guide by compositional type, volcano type, region that recommends the code to use and start. Stromboli is a nice deep degassing with changes in carbon CO2 sulfur ratio for benchmarking emissions with multi-inclusion studies to compare with. And then arc volcano with persistent variable carbon sulfur outgassing. So that's all.
That was great, thank you. Any questions or comments, either online or in the room, on what observational researchers need the codes to do? I'll advocate for Ruopehu being a, we could add the problems of a hydrothermal system on top, because Ruopehu has 20 years of gas data from GeoNet, and is an andesite. We don't have any sulfur measurements on the melt inclusions. Yeah, Jeff's fault. But we can work on that. So That would be one option. Yeah, Jeff, you can.
Yeah, I think one thing that we could look at is a well-known volcano, well-studied volcano that's got both. One's got a hydrothermal system, one's without one, and we can start trying to tease those contributions out. I think many of the really dangerous volcanoes have hydrothermal systems, but I think we need to start with probably some simplified system to then really understand all the scrubbing dynamics, which I'm not really sure is that well understood anyway. I know we know about scrubbing, but we don't necessarily know the kinetics of that process. So that's just my point of view.
Thank you for that. Anybody online want to add anything? It's been a long day. Well, actually, for the folks online, it's probably a horrible time. So that's kind of. Well, yeah. Okay, well, if there's nobody wants to comment in the room. Penny, have you had enough time?
Yeah, it's the world's most rushed thing, but we can give it.
You did fabulously.
Okay, so I've just put together kind of the 6 key points. Can you see my screen, Ari?
Yeah, it's not in presenter mode if you meant it to be.
Oh, okay, 1 second. Sorry,
That's
I'm
it.
too tired. There you go, see it now? Okay, so the number 1 point was, as Trisha raised in her talk, if the gas ratio is changed after it was being emitted, it's going to be incredibly hard for us to use our solubility models. There were some suggestions in the document of building thermodynamic models to account for hydrothermal systems to really be able to deal with that kind of after reaction, as well as incorporating sort of the diffusivity and the disequilibrium into those models. Obviously, if there's no hydrothermal system, the diffusivity is going to be key. And if there's a hydrothermal system, you may well have to be accounting for both of those, which will be complicated. The second point was really the need for volcano-specific models, how there's a lot of gas data on basaltic systems, very little on non-basaltic systems. I guess largely the eruptions are relatively rare, and when they happen, people don't really want to be that near to them. So there were suggestions of picking a few volcanoes and doing really detailed petrological case studies and any gas records we have. The problem with these being, as they erupt less frequently, we might never see an eruption in our lifetime to check the gas ratios that we are modeling and predicting. So that's a problem. In general, faster petrologists and the fact we don't have a time machine is a serious issue. So for many volcanoes, we have no gas record. So when the eruption starts, that is the first time that we will get gas. And if we want to understand that gas composition, we're probably going to need to do the petrology, but to be useful to the gas geochemists, we need to be doing that petrology like during the eruptive crisis. So finding ways we can do melt inclusion work and sulfur and chlorine and carbon measurements quicker than we are at the moment. Point 4, as we've raised with all of these, is we need more money. We need more gas geochemists at HVO. Eri probably wants more gas geochemists as well at GNS. We don't have enough drones. We don't have enough multi-gases. We need a lot of money for developing drone-based sampling strategies to really be able to get samples that we haven't been able to get yet. We need more money for experiments, and we need to be expanding codes for other volatile species and disequilibrium. And code writing takes time, and that's going to cost money to get the people employed. Hopefully, as people have mentioned, long term, so that those codes are maintained, not just like a 2-year postdoc with no kind of add-on support after that. The 5th point was access. So flying drones in national parks is challenging. Many of you might have seen Kate Laxton and Emma Liu's approach at Old Onyu Lengai of stringing things back and forth across the Cape crater to get lava samples and gas samples. Is that going to happen in a US-based national park? Probably not. So it's a lot of work for the HVO folk to do permitting and actually getting access to make the measurements that we need. And flying drones is also problematic in many sort of protected areas. And then the final point was just we are measuring chlorine, fluorine, and now bromine in the gas, and we don't have models for that at the moment. And that kind of needs to be addressed if we want to understand what we're measuring with those. So yeah, happy to take just further discussions, as that was quite a short summary.
No, that was awesome. Thank you. So yeah, is there anybody in the room who wants to comment on that, or anybody online? I would like more gas geochemists too over here. Can I come on? Sorry for the microphone.
So around our table, we were discussing where might be some interesting non-basaltic sites to try to study from a community's perspective. And the table thought that maybe Sakurajima in Japan might be a very interesting place to go, mainly because of its activity and the ease of sampling material from that volcano. It is an extremely well monitored volcano, and it would be a really interesting place to try to apply some of these models to a basaltic andesitic system. It does have lava domes at the top, so it's a pretty good it's a very good arc volcano. And in terms of a rhyolitic system, Maule in Chile is a very active system, and there's a lot of work going on down there as well. So that might be a very interesting place to look at from a silicic magma perspective.
Yeah, great options there for sure. Got another comment in the room?
Hello. So we originally were doing sulfide solubility in reduced magmas, which was relatively straightforward. And so all of this Kilauea and all this stuff, where you're mostly dealing with sulfide, is, from my perspective, quite simple. But when you're talking about intermediate magmas where they're more oxidized, when we get into that NNO plus or minus 1, you get into this really crazy area where it's sulfide and sulfate. And we've been doing some experiments there, and it turns out it's crazy, and it's really strange, and I don't even know how we're going to figure it out. Right. So I just wanted to say that when you say intermediate, to me, it's not that important that it has more silica in it. What's more important is that in these arc systems where they're more oxidized, we get into that nasty region in the middle where predicting sulfate solubilities is, I think it's almost impossible, but we should get my coworker Hugh, because he could talk for a week on this. You want to say something, Hugh?
So one of the reasons that we've been able to do sulfur is that it's quite amenable to experiments at 1 atmosphere pressure. However, you've been mentioning the halides, or at least the halogens. And I had a go a few decades ago about trying to measure the solubility of chlorine in silicate melts at 1 atmosphere, and it was a complete disaster. One of the experimental byproducts was phosgene, the First World War gas. So you have to be cognizant of lab safety. That doesn't worry me. However, more seriously, the chlorine actually stripped most of the cations out of the experimental charge. So you start with your melt containing sodium, calcium, magnesium, etc., and you just end up with a bit of silica and aluminium. It's not going to be solved anytime soon. It's just inherently difficult. People do experiments looking at saturation with a chloride type phase at high pressure, which is easy, but it doesn't answer what the activities of the chlorine gas species would be that you need for doing halogen degassing from volcanoes. Something else completely different that I just thought of when I saw this list going up is that at some point in a normal silicate mineral, there will be a finite solubility of sulfur as a sulfide anion, replacing the oxygen anions on the normal silicate lattice. And if we could crack that one, I'm talking about things that might be of up in the region of a part per million or so, then every nominally ansulfurous crystal that we could get our hands on, like an olivine, could tell us something about the sulfur fugacity, potentially.
So this is a completely, well, it's not completely unexplored. There has been a series of papers published claiming that clinopyroxene contains something like 10 to 20 parts per million of sulfur, which is huge compared to what you can analyze on an iron microprobe these days. I'm just skeptical because, in fact, they tried to analyze these things on the iron microprobe and got 0. The results were reported from X-ray absorption spectroscopic, using a synchrotron thing. And the two attempted measurements did not add up. So the paper said, well, we're going to report what we can measure, which was the X-ray absorption results. But, if the iron microprobe was coming up with 0 and your X-ray absorption was coming up with, as I say, 10 to 20 parts per million, you've got a problem. You sometimes wonder what peer review is for, but I won't go there. Nevertheless, the possibility exists, and I've been discussing this with John for decades too, that with sensitive enough iron microprobes, we should be able to see these odd anion things that are so important for volcanic degassing in the silicate or oxide minerals themselves. I've probably got a lot of other things to say too.
No, thank you. Those are great points. Any other comments? Does anybody online want to? Oh yeah, go for it. Hi, Alan.
Hi, everybody. Hope you're having a great time down there. Thank you for making this hybrid option. It's been really fantastic for those who haven't been able to get there in person. But what I actually wanted to mention is, in case folks don't know about it, there's an IAVCEI commission, like the subcommissions, one on the chemistry of volcanic gases. And the next meeting for this is going to be in 2025, I think, in Japan. So that would be a potentially wonderful opportunity for folks in the modeling and experimental community that doesn't often interface with those who measure, who are doing gas emissions, to actually have some in-person meeting and crosstalk and see how the gas side of things work. So anyway, just wanted to let you guys know that's coming down the pipe in a couple of years.
Yeah, no, that's a really great point. And then normally they just had one in Peru. Was that
in Peru,
right?
Yes. Of course, there's a lot of interest in that community in what the model, in the solubility modeling community is doing, but the number of people who actually participate in both types of activities is usually quite small.
Yeah, that's a really great point. Thank you. Any further comments? Okay, well, yeah.
Could I ask whoever it was that showed,
Do you want to come to the microphone?
well, you could just,
Oh yeah.
whoever showed those that you know about.
So Trisha, I think in your presentation you showed sulfide blebs like dissolving, like a cartoon. And John's just asking, was that like a conceptual model? Like, was it based on anything specific, or is it quite an unknown part of that process?
Trisha, was that my figure they're talking about, do you think?
Yeah, I was just going to say, I was in my talk, but it was Penny's figure, so go for it.
Awesome. Penny, do you wanna...
So that was based on some work we did at Kilauea, where we look at the copper contents with magnesium content, and we see that the copper content in the liquid don't go down with magnesium, even though we know we're sulfide saturated. So what that meant we had to do in the 1969 eruption was almost all of the copper that got sequestered from the melt had to be resorbed back into the liquid before eruption to kind of account for the fact that the copper wasn't declining. Emma Liu has a paper coming out soon looking at sulfide resorption in Holleran as well. So we do think that we see like partially resorbed sulfides, they're completely pristine in crystals and they're varying stages of breakdown in the melt. So we definitely know texturally they're breaking down in the melt. We're not really sure. We know like the copper and the nickel rich components don't break down at the same rate, but it's still like, we're still trying to do a lot of work on how that's working and what it's meaning, particularly for the metal gas signatures, like the copper and the selenium in the gas, more than like the major components we've been talking about here.
Awesome. Can I ask you to go offline with that? Because we've got to have a little wrap up on the end, but thank you.
I'll ask.
Yeah, awesome. So for the last little bit of time, we wanted to talk a little bit about next steps. So at the beginning, I showed that the outputs that we were thinking were a kind of workshop report. So taking all of the great ideas that you've all contributed, and we'll put them into some kind of summary, and we will send that out to everybody so people can have a look at it and give some comment. We also have put a form out to those who can't make this workshop to give feedback on similar topics that we've discussed today, to try and get more input from the community. And then we will also hopefully, and we'd put that on probably Earth Archive as a place for that kind of a report. And then the other thing we were hoping to do was, based on those kind of benchmarking calculations, was to maybe write something up on the model comparison work to try and show how all the water and the CO2 models are doing, and the new sulfur models, and hopefully get some involvement from Decompress as well, which is a model we haven't shown at all today, but is one of the more accessible models that people do use. Penny or Echo, is there any other output thoughts we had? No, those are the two, right? Cool, yeah, so we just wanted some input from everyone about if people thought there was another kind of output that we should look towards. If there's anybody who would like to kind of be a little bit more involved with helping out with that write-up, then feel free to get in contact with any of us. But yeah, basically, if there was another kind of output that would be useful, and any thoughts on that, either in the room or online? No?
This is Trisha. I know
yeah, hi.
Kendra already signed off, but she had texted me. She was thinking big picture. Like NSF has given a lot of money to interdisciplinary efforts like Converse, and she, was thinking, can we just get money from somewhere and really attack, at least the gaps that we've identified, like the compositional gaps, and just get group money, like make some sort of volatile sub-Converse kind of thing with a lot of the people here. Anyway, yeah, that was what Kendra texted. She's not here, so I figured I'd throw that out there.
No, that's a really great thing. I think in the UK, there was a consortium on volatiles, but I think it was on mantle volatiles. Margaret, if you're there, remember that?
Hi, yeah, it was on deep volatiles. There were 3 consortium grants for 5 years. I think they have all expired now. So the outputs of that will be either emerged or emerging. The one that I was most familiar with was led by Oxford, and they did quite a lot of modelling on the deep halogen cycling, as I recall.
Interesting.
Yeah.
I guess another big grant that was the Deep Carbon Observatory, which had some work on specifically carbon in these systems. Because yeah, a lot of it came down to money, right?
Because DCO was Sloan, right? So it was like massive.
Yeah. Yeah, that was a decade. It was 10 years of funding for that. Yeah, something I'm interested in is very much the intermediate magma compositions, so that we can interpret the kind of measurements that we make for volcano monitoring. Because I was in a meeting and the geophysicists are like, oh, so like how accurate is your estimate of the depth from the carbon to sulfur ratio? And I was like, not like for a system like Ruapehu with a hydrothermal system on top, and it being like an intermediate volcano, we can qualitatively interpret those changes in carbon to sulfur, but there's no way we can be accurate, which from a monitoring standpoint is more what I care about, is the accuracy. And that's definitely been a big change for me, moving from kind of academia to the monitoring space. In academia, patterns are fine, and kind of the broad scale changes. The model I showed does really well for a Hawaiian tholite at 1200 degrees C. That's what I kind of started with, but like those general patterns are really useful for understanding how the system evolves, but not when we want to then apply it to specific systems. But yeah. Yeah?
I think you just touched on something I've been mentioning in the groups that I've been in, which is the reason why we do this. I think it would be worthwhile people thinking about why we do and we care about solubility, which to me is on the sort of the edge of actually providing warnings to people, is to keep people safe. So if whatever grants or applications go in, I think it's really key that you kind of keep people in mind, and then you have the monitoring as the ultimate outcome. So, or improving monitoring as the outcome. So it doesn't need to be all on the applied end, because there's a lot of fundamental stuff we need to know, and we've talked about that today. But I think whatever grants you apply for, and I think it'd be nice if we have a collaborative approach with, you know, putting in grants here and here and here. It might not be just one system that we look at and really close, with a really close eye. We might want to pick a few disparate volcanoes around the world and really turn them into lab volcanoes, that we've got the local people involved, the local agency involved, but not just there to host international helicopter science, but it's actually to be deeply involved with it. So I think that would be how I'd frame it. And I think there's seemingly willingness in this room even, and definitely from the people who monitor the volcanoes, to really try and answer a lot of these questions, to really close that gap so we can get closer to being, I think, the better cousin of the geophysicists who have their less than 1 hertz kind of, or more than 1 hertz data coming in, streaming to their computers, whereas geochemists always have to go out, collect that sample, do a whole bunch of work, and then that's like, okay, we'll go out next month. So I think there's just a series of things that I wanted to mention there, but just keep the kind of people side in mind, so it's not just purely academic.
Yeah, great points there. Any other comments? Okay. Well, in that case, we can wrap up. I just want to close out with a few things. So firstly, as I said, we'll be collating everything together and we'll be sending it out to everyone who signed up and others who are interested. And we really love your feedback on that. We also might put together just a little like feedback form on how the kind of running of the workshop went, so that if we want to run similar things in the future, we kind of know what worked and we know what didn't work. For everyone in the room, thank you so much for wearing masks throughout. That's really great. I know it can be quite stuffy, but we don't want to catch COVID. Thank you everyone online who's stuck around for any or part of it. I know it's probably a terrible time for most of you, wherever you are. So we really appreciate you coming on the like Aotearoa schedule, which isn't very nice for everybody else. Maybe slight payback for when we've had to go the other way. I'd like to thank everyone who helped to organize this. So Jeff, who's been here in the room today, and also online, we had Echo, Penny, and Kyla, who have been working fabulously to work out all the breakout rooms. And oh, thank you for everyone to come up to the mic so that everyone online can also hear. I think it's been really great to have virtual, to have a hybrid system, and especially as the weather meant that people couldn't turn up. So I think that's been really great. Any other comments from Penny, or I don't think Kyla's online, or Echo?
And just thanks to all our invited speakers, including Margaret, who must be up well past midnight now. So thank you, Margaret, for joining us, and Trisha and everyone else. Thanks.
Yes, thank you. That's a great point that I had not brought up. So yeah, really appreciate that. Okay.
Oh, sorry, and thank you, Chen. Oh, sorry, I didn't realize you were here.
Chen popped out and has come back, so thank you for rejoining us for the end. So awesome. So I think we can close out there. Jeff, for those in the room, Jeff's going to give a little bit of a quick explanation of the porphyry that's going to happen in about an hour and a half's time. So if you guys just stick around for 5 minutes. But yeah, thank you all for coming, and we'll be emailing you soon. See ya.
Thanks.